minimal sufficiency. And so the idea is that there are different levels of compression achieved that can be achieved by sufficient statistic. And if you want to find the most compression, so the way we look at it is that we can use functions to measure your compression information. So if you have a statistic t, for example, when you form t squared, you lose information anytime you form a function, unless that function is injected. And so we just introduced this notation that we write t is smaller than s in this order if there exists a function such that t can be written as f of s for almost every like under almost everywhere under the probability measures that we consider in the model. So we're going to ignore this part for the majority of the discussion. And so this is simply means that t can be written as a function of s. And so you say a statistic is minimal if it's sufficient, t is sufficient, and if I pick any other sufficient statistic s, t can be written as a function of s. Okay, so the second condition is basically saying that t has more compression or achieves more compression, is smaller than s in this information sense. So we did an example, which I'm not going to go through, or just presented the example. So we wanted to show this, that basically the likelihood ratio function is minimal sufficient. So the likelihood ratio between two parameters is this. So you take the density divided with the current observation for two different parameters. So you have a parametric family of densities to look at two of them, compare them basically. What is the likelihood, in a sense, of the data under the X versus under the other class? And so the idea is that by factorization theorem, we'll just see this shortly, that this can be written as a function of any other sufficient statistic. So this automatically satisfies the second criteria, or criterion. And it's just that it may not itself be sufficient. But if, let's say, my parameter space is finite, I can just apply any parameter, all the possible parameters, and hope that once I look at all these ratios, then that would give me a sufficient statistic. And that is indeed the case if we are in this DCS family, dominated concept. Yes.
I'm a little bit hard to understand with they're not sparse. In, like, for example, in the normal distribution setting with theta, you have a mean theta secant squared.
It depends on the parameter. So if you remember, we just have a general parametric family. So this could be, so this is basically the density of p theta. So let's say if p theta, for example, if p theta is normal between theta and 1, then this p theta of x is 1 over root 2 pi e to the negative x minus theta squared over 2. Okay. But it could be like a different family. So you can have like a mu and sigma squared, all mu and sigma squared theta, then you have a two-dimensional parameter. So whatever you want, this is very general. We'll do this example later. So this is usually people don't restrict data to be finite, but let's say if I restrict my parameter space, remember the parameter space is omega, to be theta naught and theta 1. Okay, so this is really a binary parameter space, effectively hypothesis testing. Basically, I want to test whether the data is coming from a normal mean theta naught or a normal mean theta 1. So theta belongs to this. Then I really have one likelihood ratio, theta one. Theta nine.
So these are possible values of theta you take.
Yes, yes, yes. All the possible values in the parameter space, yes, are candidates. So what we're gonna look at is, for the most part, for simplicity, the case where this parameter space has k plus one values, okay, finitely many values. Okay. These are this the candidate parameters. Remember, there's a parameter family of distributions parameterized by parameters of these values and so on. Here's an example and many other examples. Sounds good. Okay, and then if we have a DCS family, the DCS family, for example, if the support is entirely aligned, no matter what parameter I choose, so it has common support. So I'm not going to worry about which one I take to with the denominator. So pick one, whatever whichever one. This is what we call it normal everything here, take a knot, and then I form the ratio. And then when I sort of collect enough of that, it becomes sufficient. And turns out actually in this Gaussian case, even if the parameter space contains all the real value parameters, just taking two is enough. Taking these two, we'll talk about this, but it's enough to take two parameters. So one to form one ratio that is equal to the other. We don't want to put it in that pattern. But in general, this is not sufficient, so we keep adding up. So I just want to like sort of prove this. Okay, so we're gonna like spend a bunch of slides on this, so don't worry if this is not clear. So that's the plan, okay? So to make it more clear, let me start with this useful lemma. So I'm gonna call this L theta of x, and then so I'm gonna drop x. So for any given theta, so fixed theta not that parameter, right? For any given theta, this is this quantity is gonna be the value of the statistic. Okay. Just take this theta not, and then a value of a particular theta is just a function of x. It's a statistic. So the idea is not that in these families, the bond for equivalent. So U is sufficient for the family is equivalent to saying that L theta is a function of U for any theta. So that's basically what I mentioned here. So this is L theta. This is a bit more because it's saying that it's equivalent. It is equivalent. So U is sufficient and all. This is all the U is sufficient. And the way to show it is really simply by factorization theorem. So assume U is sufficient. U is sufficient. Then I can write P theta of x as G theta of U of x, H of x for some G theta by factorization theorem, right? If you recall. Then from this, I'm just going to apply this to both theta. This holds for all theta. So in particular, if I evaluate theta naught and divide, so you can just in your head divide it, you get G theta U of x divided by G theta naught of U of x, and H cancels out. Okay. And so you can see this whole thing is a function of U of x. So this is really a function depends on theta and theta naught, but of U of x. Okay. So we proved that this L theta of x, or L theta, the way I write it is, this L theta of x is really a function of B. So prove A implies B, so this holds for any theta. So this function is going to change for different theta, but for any specific theta, this is the function of U of x. Okay? A implies B. Right. how do we show that B implies A? We just reverse this argument. So suppose B holds, then I can write L theta of X as a function of U of X. This function potentially depends on theta and theta naught. Otherwise, there is this function. Okay. Now I know that this is by definition that. So that's by definition. And then you multiply both sides, you get P theta of X is F theta theta naught of U of X, P theta naught of X. So this is really H of X, doesn't depend on theta. And this is some G theta of U. So theta naught is fixed. So this holds for any theta. So really we have this factorization. So we have the factorization, hence U has to be sufficient by factorization theorem. Yes.
So L in itself is not sufficient. But if you have a lot of U, we get solution.
Yeah, we get to that, but at this point, it's just that it's L is a statistic for any data, and it's a function of U. If U is sufficient.
This doesn't imply that L is sufficient.
I mean, we get to it. So that's yeah.
Oh,
Yes, yes. Because yeah, like just one little step to, because for each one, so this step that this is, yeah, let me get to that one, yeah, you'll see. It's almost there, but just one more step and you'll see. It's a little bit tricky, but this is quite simple. So you have to be able to like, hopefully do it for yourself. It's just almost like rewriting of the factorization theorem. Factorization theorem goes both ways. And so this is just, you can see the division by the theta naught is kind of rid of the schedule of just within the theta naught. Theta. Okay, so is this sort of clear? U is sufficient if and only if, when I form this L theta, that L theta is a function of U for any theta. So the next slide is just rephrasing this a little bit. So instead of this B, so this is saying this L theta is a function of U for any S, sorry, for any theta. So this is equivalent to saying that if I look at L theta, let's say as a vector, so this contains all the L thetas. So it's not a vector form. So imagine this boldface L is just L theta 0 with theta 1, L theta 2 of X, dot L theta K of X, which I like shorthand notation, I write it as that. And implicitly, we can also imagine that theta is infinite dimensional. So collect all of them. In the continuous case, it would be a function. In the discrete case, it would be a vector. So this little observation here is saying that if R is a function of U, S is a function of U, then R and S that will carry is a function of U. And if R and S is a function of U, then individually they're a function of which they can create this. So compose this to function of basis for the first coordinate. So this is like topology in a sense. So this one is like that. So this is saying all the coordinates of this guy are functions of U. So as a whole, the vector is a function of U. Okay, so this is just restatement of that. Okay. If this makes sense, then you're in business now. So U is sufficient. If and only L is a function of U. L as the entire vector or entire function. Okay. So now from this lemma, we can conclude that this is whole phase L itself is sufficient. Why is it sufficient? I have a like an equivalent characterization of sufficiency. Yes.
So to answer the function, the question why is sufficient, it's because the two slides before them mistakenly collected as they are sufficient.
Right, let's say I give you this level, right? I haven't proven that if you collect enough of them, it's sufficient, right? So that was just pre, but let's say I prove this, sort of. Can I conclude from this that L is sufficient? So this gives you a way of checking whether a statistic is sufficient. If I give you a statistic U, if you want to check if it's sufficient, you can use the definition, you can use the factorization theorem, or you can use this. How do I use it if I want to verify that U is sufficient? Because it's a clear factorization. I'm going to check whether I can run L as a function of U. Now let's say I want to check whether L itself is sufficient. Can I use this result? Yes.
Plotting L for XB.
Yes, just plug in L for U. So L is a function of L. So L has to be sufficient. B implies A applied with U equal L.
U equals L.
Take U, so this holds for any U. If L is the same, if this holds, if E holds, then A holds, and this holds for any U. Plug in L here. So L is a function of L implies that L is such. So L really is a function of L, anything is a function of itself. So it has to be sufficient. Okay. It takes a while to, but it's just true.
Because L is a function of itself.
Yes, because you can write anything as the identity function of itself. So once you have a characterization like this, then the first thing that you can apply to is L itself, and this proves that L is sufficient. Yes.
Could you explain one more time how A implies B?
A applies B is like we proved it here. A implies B is by factorization theorem. So you talk about A implies B. So if you do the coefficient, then you have a factorization, and then we form this, and then you end up proving that. So this is the same lemma, I just rewrote B slightly differently. So this 3 is just 2. Okay, 2 we prove. 3 I convinced you that it's just, instead of saying all the coordinates is a function of U, I can just say this entire vector is a function because it's equivalent. Now, once you have 3, and you stare at it for a while, you realize that this also proves that L is sufficient. 2 and 3. Yeah.
So 2 proves that L theta is sufficient, and then L is a function of.
No. 2 is just saying, it's just an equivalence. So 2 is the same as 3. So what is, like, let's say you either talk, let's either talk about 2 or 3. Okay. So none of them is like the face of it, it doesn't say anything about in your statistic, it just says that if this holds, then the other one holds, if the other one holds. So it's an equivalent characterization of sufficiency. But you can apply it to L itself to verify its consistency. And this proves that L itself is sufficient, not consistent, sufficiency. Okay? On the face of it, it's not telling you any statistic is sufficient, but really like an immediate conclusion is that. Yes.
This might add to this concept, but I was wondering, you're showing lemma 3 L is sufficient, but we did not say that L theta is sufficient.
L theta is not necessarily sufficient, yes, because if we need to delete this, in order for me to show that L theta, one of them is sufficient, I have to be able to write the entire vector as a function of that. Okay. So we have this entire function, like a vector function, we can write that function, that one as a function of just one coordinate, and that coordinate would be sufficient, so this is not necessarily true. Right.
We say L, not L.
Yeah, the entire L itself is sufficient. Yes. Okay.
Here's me, what
Yeah.
Very crucial.
Yeah,
Yeah.
this is B implies A. So I was proving. There's no integration, so let me maybe put this above here, it would be a little more clear. So suppose A holds. So this implies A by its definition. Now suppose B holds, then this implies that. So once we have that, this is implies that U is sufficient by factorization theorem. Right.
So why do we see considering and allocate as a
Can you say that again?
because you just said for B to be implies we also need to be also trying to allocate as a
No, in order to show that B implies A, after you assume that allocate in the function of B, and then show U is sufficient. That's what it is. So we assume that allocate can be written as a function of U, then I show that P theta has this factor as 4. This is not integral, it's just F. Right? You should have written it a little bit more. So this implies P theta of X is F theta and theta naught of U of X times P theta naught of X. And this holds for all theta. And then this implies that. Implies that U is sufficient, right? Yes.
You said there's 3 ways of checking, like equivalent ways of checking if
Yes.
the statistic is sufficient. One was factorization theorem, another one was seeing if you can write the likelihood ratio as a function of the statistic.
Yes.
What was the third?
The first one actually is
Yeah.
like by definition. So just look at the conditional distribution of X given T. Then the factorization theorem. This is really factorization theorem in disguise. So
Yeah.
okay. Yeah. That's yeah.
So what happened if this is
I'm gonna tell you at the end. Let's figure out what happens if it holds. Then I'm gonna talk about that. So this one fails. So this lemma fails. Do I have it somewhere? I do have it here. So then when we see a scale, A is still implied, we go B not necessarily implied. We'll see examples. Right? But if PCS holds, this is it can only so you run into like you need multiplication and division by zeros. So this argument would fall apart. So if you have PCS, I can do all of this on the support, the cone support. Anything else, you can't support these as positive. So I can easily divide and multiply. If it happens that the support is not common, it could be that this is positive, but this is not positive. That's what I have to consider at least the union of the support. Right? So these arguments fail. Well, some parts fail. You can try to convince yourself. But we'll see an example at the end. Yeah.
Still, I'm not clear when you do B to A, like why L theta is sufficient.
B doesn't say L theta is sufficient. B just says, sorry, B to A doesn't say L theta is sufficient. B to A implies that you, in order to show B to A, you assume B, you show that U is sufficient. Right? But then your question is,
Because we could.
so once you have this, then you plug, like, put it back together like this. So if you believe that B that I wrote there is just this exact B, now you look at this, this is giving you an equivalent characterization of sufficiency. U is sufficient if B holds. Okay, so now I want to verify whether L itself is sufficient. I can plug it into B for U, right? in the function itself, so it goes. It looks like tautology, but there is some argument going on here, right? So once you show that something like this holds, it immediately implies that L itself is sufficient. Sounds good. But if you understand this, we already have proven that L is minimal sufficient as well. So the definition, so the next step is to show that L is minimal sufficient. The definition is that for whatever sufficient statistic, I should be able to write L as a function of U. So this is saying that that's possible, and also saying that L itself is sufficient. So L is sufficient, and for any sufficient U, I can write L as a function of U because that's A implies B. So B implies A gives you that L is sufficient. A implies B, saying that L can be written as a function of any sufficient statistic. So A implies B says that L can be written as a function of any sufficient statistic. Okay, B implies A. Itself implies it's a consequencer that L is sufficient. So I have a statistic which is sufficient, and any other sufficient statistic, if I give you any other sufficient statistic, it can be written as a function of it. So it's by definition minimal sufficient. Yes.
I have a question. When the DCS failed value, assume that I have P theta 0, such that its supported is all the union of the other probability distributions supported. Then
Is it
where
going
the
to be?
theorem still holds.
So if you have a P theta naught that contains the support is contained like the union of
all the other probability distributions. And then I write the L as P theta 1 over P theta 0, P theta 2 over P theta 0, and so on. And
right.
then it seems that this L is still solution to that.
That seems to be true. If you're not wrong, yes, I think this is good enough. If one of them has support that contains all of them, right? Just verify, because then I can divide this everyone by this. And one of the issues is like canceling here, and canceling would happen. Does it happen? So if it does seem to work, but this part is a little bit worrisome because yes, okay, so let's say if there's an edge here, which I'm canceling. So this edge cannot be 0. Because if it's 0, so let's say I'm going to support P theta naught, then this edge cannot be 0 because this doesn't depend on theta naught, right? So it has to be positive. Otherwise, so I can also cancel. It seems to work. It does seem to work to me. Yeah, the real issue is when one of them is like there's no one that can so all of them are like have some overlap and some non-overlap. Then it's going to be problematic. But it seems like in the case that you're mentioning, this should be true. So once this holds, then the rest follows, right? So just double check this for yourself. I think it holds. Right, right. Good point. Any other questions? Yes.
So
because B implies A. And because L is.
Yes.
L is.
Yes, yes, yeah, it's easier to see it here, so like. B implies A, and in this case, it's not a function itself. So it is sufficient. Right? So once you understand this, then you also see like that we have proven minimal sufficiency. So we have actually proved this. So the argument I gave you, just basically A implies B and B implies A give you the two sides. So this L itself is minimal. So the fact that L itself is sufficient is follows from B implies A applied with U equal L. Sounds good? Yes.
The number of A terms here.
Right.
How do we know how many there are in this support, say, is just few numbers?
So what I'm doing here is I'm assuming that the actual parameter space is there. Like this fine, the entire parameter space is fine. So that's part of the problem statement. I'm not saying K theta, right?
So we know the number.
Yes. So that's for the easy next part. But this argument also works if sort of works. If you ignore, like if this is a function. So the only there's nothing about this being finite in the argument that they did.
Oh, so
Except-
two functions.
This would be a function itself, the entire function, the entire vector function. The only issue is there's one thing that I like ignored, and this is like this little problematic almost everywhere P. So all these statements that I mentioned hold almost everywhere P. And so if you have countably many of them, it's fine in measure T. If you have uncountably many null sets, I'm trying to like accommodate uncountably many things would be problematic. So if you ignore this, what I said is true. If you don't ignore it, you have to like work yourself towards it, but it seems to be still true. So if you look at Kinari, I'm going to give you like formal statements. I just did it in the finite case, or actually like it would be like all the things that I mentioned would work if it's like uncountably many, the parameter space has countably many members. And there are various like ways of stating formal statements. I'm going to give you some of them. And if you really are interested in the formal statements, those would do. But the reason why I'm reading is just that you can take it. Just let's understand the ideas, then I'll give you the formal. So this L is minimal sufficient. And now we're going to massage it into many different forms. You can say it in different ways. First, I mean, like a corollary of this is that I can say that T is minimal sufficient, a general statistic is minimal sufficient, if T is sufficient, and then I can replace the second criteria as T being a function of L. Right? Why can I do this? Because by that proposition, I know that U itself is a function of any sufficient statistic or by minimal sufficiency. So in order to show that T is a function of any sufficient statistic, it is enough that this holds, that T is a function of L because L is a function of any other sufficient statistic. And also, it's like one thing, if and only because L itself is sufficient. If T is going to be a function of any sufficient statistic, it has to be a function of L. Right? But being a function of L is enough to be a function of any other sufficient statistic because this itself is a function. Okay. So it's like L is at the bottom of hierarchy. L is a function of any sufficient statistic like candidate U. Okay, if T is supposed to be a function of any sufficient statistic, it has to be a function of L itself, because this is also sufficient. So T is going to be a function of this, but this is a function of U, so T is going to be a function of U as well. So this is enough. Sufficient enough. Like it's necessary and sufficient for T to be a function of any other sufficient sense. Yes.
I'm sorry, so in corollary one. Is L just an arbitrary?
No.
Sufficiency?
No, L is this quantity, this particular likelihood ratio. L is this guy. L is going to be the likelihood ratio collected across all thetas. So L is going to be for us this quantity. T theta.
So
L is L theta in omega, and L theta is just P theta of X divided by PF. So this particular statistic, which is the likelihood ratio process, if you want.
so L is an arbitrary L sub theta.
There's nothing arbitrary here. L exactly this. So you have it
between L sub theta.
So, okay, so this is like the difference between x1, x2, x3, and the difference like the vector. So this is the vector, these are the coordinates, right? That's that makes sense? Yes.
But L is the minimum conditional.
Yes.
And the definition says that T is minimum sufficient if T is less than S for any sufficient statistic. So I was a little confused. How can in slide 16, how can we have a statistic that's less than our minimum sufficient?
Right, so it's going to be a bijection base. So if this whole, because there is also going to be a function of T, there is going to be a bijection between. So really, T is minimal sufficient. If it's sufficient, it's in bijection with the minimal sufficiency. The minimal sufficiency is, as I mentioned, it's like you can see now that it's sort of unique up to bijection. So if the minimal sufficient, you have to be sufficient, you have to be a function of any other sufficiency, including L. But once you're a function of L, then you're a function of any other sufficiency. This thing, and in particular, this is also a minimal sufficient, so this is going to be also a function of that, so it's like back and forth. But this statement just helps you establish it, so you don't have to show that. Actually, okay. So now that we're there, I can also replace this with L being less than or equal to T. That is easier to see. Why? Because this is this condition here. Right? In order to show that T is sufficient, I can say that L is a function. Okay, so I can just replace this as equivalent statement of this corollary is that T is not sufficient, you can only L is the function of T and T is a function. And that's sort of, I haven't have it here, but it's like another one of the things that you can say. Corollary 1.5, T is minimal sufficient. If and only if L is a function of T and T is a function of L. So T is in sort of bijection with L. Yes.
So in lemma 2, you learn that the scalar L, this one L, is a function of any sufficient statistic.
Yes.
But then in lemma 3, you learn the factor L.
Yeah, so if any one of them is a function of a sufficient statistic, then as a vector, they're gonna be a function of.
Yeah, but I feel like just looking at number two, I feel like that's equivalent with if the scalar of this one is also unlimited.
No, it's not, because let's say I have two L theta, so let's say I have like the space is theta 1, theta 2, theta 0, theta 1, theta 2. Okay. So my L would have two coordinates, L theta 1 and L theta 2. Right? So let's say I look at this. Okay, so this is a function of any sufficient statistic U, right? Right. And so then what are you saying? So you're saying this is enough for U to be sufficient?
I mean, for L theta one.
To be minimal sufficient. So L theta, so for L for so this is true for any sufficient service. But in order for me to, for example, conclude that this is sufficient, so this has to be, I should be able to put it here. And this has to hold for all theta. In particular, I should be able to say that L theta 1 is less than or equal to L theta 1, which is true, and then L theta 2 is less than or equal to L theta 1. This is my U now. This has to hold for all theta, which may not, this may not be true. But if I can show this, then yes, that particular coordinate is.
And in our proof, then we use for all.
For all theta is where you need, so B implies A, you need this factorization theorem to hold for all theta. Okay, it doesn't, like if you just hold for one theta, that's not factorization. Yeah, no. Okay. Yeah, this takes a while to wrap your heads around, but it's not super difficult. It's just that it's a little bit tricky. So
Why do this happen with DCF?
because of the divisions here. Right. So if I'm let's say I'm going to try to establish this, but this has to hold for any x in the support, right? If there is an x in the support such as this is 0, and it's not, then that particular one cannot be written in this, and divide it and multiply. Okay. Sounds good. There was some example. What was your name, by the way? Yes.
Oh yeah, my name is Hongzhi Ho.
Hongju Ho. Okay. So the example given by Hongju Ho is like an example which is not ECS, but this still works, it seems. The case where there is a theta naught for which this has a support that contains all the other ones. Then I don't have to worry, I can work on the support of that. This is always going to be positive, so this seems to work. So that one, as an exercise, try to write it down, just make sure. But DCS just simplifies everything, okay? But that was a good point, so maybe. Exercise. It seems that everything goes true if we drop the ECS assumption, but have now a particular theta naught in omega such that the support of theta naught contains the union of the support of P theta for all theta. Something like support of P theta naught includes union theta in omega support. P theta seems to be okay. So I'll let you think about these implications, but this is another implication. So T is minimal sufficient if T is a function of L is a function of T and T is a function of L. This holds true for any minimal sufficient statistic. Once you establish a minimal sufficient statistic, in order to show that something else is minimal sufficient, you just have to establish a bijection. This is not specific to this particular L. Once you have a minimal sufficient statistic, if you think about it, it's just enough to have T is a function of that, and that is a function of T, then automatically this implies minimal sufficiency. Okay. Another characterization, so the same thing I can rewrite. So this, like T being a function of L, this last, the second one, can be written as this conditional statement. So pick any X and Y. If the X and Y are mapped to the same point by L, then they have to be mapped to the same point by T. So the advantage of this is that there is no specific function, but it's just implication. Once the implication holds, then it implies that there exists a function, and that's LTT. Again, if you think about this, this is really a property of the definition of functions. So L of X equal L of Y implies T of X. So this entire thing itself implies there exists a function such that L of X is a function of T of X. The reason is sort of, you have to do this pictorial proof if you want. You have these points, let's say, I don't know. So yeah. All right. Then T of X is a function of L of X. So what it's saying is that, let's say I have this implication. So whenever L maps two things to the same point here, okay, not this. Maybe three things. So imagine this is so these Tx and Lx can have different domains. So this is X. Let's say L maps things to they should be right. Okay, so let's say, okay, this is so let's say L maps these two to the same point. So that's L, and then maps this here. If it turns out that these 2 points are mapped by T to different points, then this T cannot be written as a function of L, because once I go to this, I use the distinction of X and Y, and then I can apply a function to this to get back these 2 points. But whenever this happens, if whenever this X and Y go to the same thing, T also sends them to the same thing. It doesn't, the code related to them. So whenever this happens, then I can map this just to that, and then I would get a function. Okay, so I can just here map this to that. And the other one, let's say in this case, T maps it to somewhere else. I just map this guy to this. So that would be my F. I can write composition L and F in T. Right? So if you think about this kind of picture, it becomes sort of obvious that this is sort of equivalent. So T can be written as a function of F. As a function of L, if and only if whenever L maps things to the same thing, T has to map into the same thing. Another way of saying this, again, this is another characterization, is that the level sets of L are included in the level sets of T, or the level sets of T are coincident with L. Let's take this, and then think about this if you want. But this is the characterization that I'm going to replace the second criteria of it. Okay. So T is minimal sufficient for Odysseus family. T is sufficient, and this implication holds. Okay. And see, since the top one is also equivalent to this. So yeah, top one is also equivalent to this, and this is also equivalent to T of X equal T of Y implies L of X, L of Y, because it's the other way around. So I can just combine them saying that T is not sufficient if and only whenever L is equal to Y, T of X is equal to T Y, and vice versa. So this is basically if and only if, another version of this thing that we wrote here. In any case, you can write it in many different forms, okay, depending on how like you want to characterize this, and then or how you want to characterize sufficiency. You can write sufficiency in many different ways. You can write this in many different ways. Then we look at multiple versions of this. So this is, for example, this is a actually a result in Keener with all the bells and whistles. So maybe this is like 2.11. And it's actually not written in this fashion. It's written, this one is replaced with another equivalent characterization, which is this. So L of X theta proportional to Ly of theta. So what is L of X? L of X is really the likelihood. So this L, so L of X is P theta of X divided by P theta naught of X. This is going to be equal to P theta of Y. So this condition Lx is equal to Ly is equivalent to, this is just their definition. So this is equivalent to saying that P theta of X can be written as, so this holds for, sorry, let's do this better. So this is the entire thing. So Lx is all the coordinates. So this is equivalent to P theta of X divided by P theta naught of X equal to P theta of Y divided by P theta naught of Y for all theta. And so if I rearrange, I get P theta naught of X divided by P theta naught of Y, P theta of Y for all theta. So if you look at it as a function of theta, this thing as a function of theta is proportional to P theta of Y for all theta. And this is really the likelihood. So you say the likelihood is proportional. So the likelihood functions are proportional for two of these data. So whenever you take two data points, if the likelihood functions are proportional, then it means that the likelihood ratios are equal. And so I can say that I replace this with Lx theta proportional to Ly theta. That's the Keener's version. So if whenever Lx theta is proportional to Ly theta, implies that Pr is equal to Py, then Q is sufficient, then Q is equal. So that's what the way he writes it. That's just another characterization. So likelihood ratios being equal, it means the likelihood functions are proportional up to constants. Sounds good. So let's see an example. So there are a lot of characterizations, but it all boils down to just what I mentioned, that this likelihood ratio is minimal sufficient. It's just that different ways of writing it. So let me show you how this can be applied. So let's work with this corollary 2. So we want to say that T is minimal sufficient. In order to show that, I'm going to have to say that T is sufficient, which is really defined. And then I'm going to assume that the likelihood is proportional for 2 data points, X and Y, and then I'm going to assume that T of X is equal to T of Y. So let's do this to see the example. So suppose I have x1 up to xn, IID p theta from f of x minus theta, f of x is that exponential. So this is the location family that we did. So I'm going to look at the likelihood ratio, sorry, the likelihood function. So the likelihood function, again, if you recall, it's just the density viewed as a function of theta. So the density is just by definition, the way that we did it is that. So it's going to be c e to the negative theta x minus theta squared. So that's for a single data point. So let's say for I. And then I have to take a product because I'm looking at the joint. So I get this, I from 1 to n. So this is going to be, so p theta of x, which is like all the x's, is equal to that. And this is like c to the n e to the negative beta summation xi minus theta squared. Okay, so that's really p theta of x in our case. Right, so that's the do it here. That's really what that's the density, the likelihood I can draw the constant. So I can look at the this is proportional up to constant to e to the negative beta summation I from 1 to this. I can drop the constant there. And in fact, I can expand. So this is going to be x. Let me do that better. So let's expand. This is like Cn. There's going to be, if I expand this, there's going to be e to the negative beta, so I can put 1 to n xi squared, which I'm going to also put as a constant, I from 1 to n xi squared, and then e to the negative beta n theta squared, something like that, right? Let's put beta here. N theta squared minus 2 theta summation xi. Right. So that's a constant. It's proportional to e to the negative beta. Or let's say beta 2 theta sigma xi I from 1 to n minus n theta squared. Sort of. Okay. Yeah.
So like essentially just that's same thing, but we're just
Yes, you look at it as a function of x for as a function of theta for
it's the same formulation. Like it's still c to n e to negative beta summation.
right, e to the negative beta. But when you usually look at the likelihood, because you look at the function of theta, and because it's usually like matters of the multiplicative factor, as we have for the tree. So the constant multiplicative factors, we don't care. In particular, so that they have to compute the maximum likelihood. Maximizing this equivalent to maximizing this one. Right. And so by sufficiency, more matters in this part. So usually then people define the likelihood up to constants. So it's like the density. You as a function of theta, up to a multiplicative factor. So that's sort of the likelihood. In any case, that's my likelihood. So that's like L x theta is proportional to something like that. And I want to say that whenever L, so x here is like all the, let's little x here is like all the coordinates. Okay, and the way that it disappears is somewhere. So this is the function of x. This is sort of my t of x here. Because in this family, the normal family, we know that t of x is sufficient. I would have proved that it's minimal sufficient. So L of x, Lx of theta, and we can have this. I wasn't sure that if I set this equal, well, let's say if Lx theta is proportional to Ly theta, then it implies that t of x has to be equal to t of y. And I'll let you figure that out for yourself. But that's in fact the case. Okay. An easier way of saying it, instead of saying what I would do myself is like look at this and see I can determine the shape of this line like this. With given this, I know the entire direction. Okay. So once it fixes up to the constant it has it's completely determined. So this means that this has to be true. Because otherwise, yeah, so I'll have to think about it. But the easiest way of seeing that this is the case is that you look at this, and then, and I completely write down this, or like the shape of it up to the constant base. By knowing this. So if what this is saying is that if, yeah, so this argument is immediately right. So the shape of this is immediately determined by this is actually the argument. If you want to do it, like say that this is, let's say, set this proportional to, so this is proportional to Ly of theta. So this set is equal to c times the same thing for t of y, and then do the calculation try to show that t of x is equal to t of y. What I'm doing here is a little simpler. From all the discussion, the idea is that this likelihood is minimal sufficient. So if I can reconstruct this of the multiplicative factor by a statistic, but in violation to this, then I'm done. And so you can see that this is in violation of t of x. So once I have t of x, I know this entire function. If I have this entire function, I can get t of x from differentiation. So I can take, for example, log, and I can differentiate and so the shape of the likelihood is t of x, and the t of x is the shape of the likelihood. So that actually proves that both sufficiency and minimal sufficiency. So this argument that I'm doing here is a little better. So first you see that up to multiple factors like that. Actually, it's not good. And then we look at the log, which means let's take the log. When you take the log, you make the log likelihood, it has to be determined up to additive constants. And so the shape is completely determined by this, by this part. And we can expand it, and this part, this is the quadratic, completely determined by this. If I have a quadratic function, if you like this form, if you give me this, I can take the part of the function. And if you give me the function, I can extract this by the derivative, by the derivative is equal to 0, I can cover that. So this is in addition to the likelihood shape, and this in addition to this, so these were in addition. And so the sum has to be minimal sufficient. But if you really want to try your hand at this, you got a little bit more clear. Sort of clear. The last piece was if you understand this argument, your life will be a lot easier. But otherwise, you can do that. Once you form the likelihood ratio, let's say the likelihood function, try to see if you can reconstruct this by doing this back and forth. And here's an example that shows you how it's done when there's no closed form. So if I look at the alpha equal 1 case, that's alpha equal 2, that's alpha equal 1, that's the Laplace pattern. That was the case that we mentioned that the order of statistics minimum. So I want to prove that the order of statistics minimum is sufficient. You can go through writing this instead of power 2 here, you can have some values. And so the likelihood to be proportional to e to the negative beta, and so we should have some values here. So that's what we get here. So that's going to be my likelihood. This is completely determined up to the mostly process by this one dimension by x minus this function. Okay. And so you can say that this function is minimal sufficient because if I have this, I can raise it to the power e to the negative beta up to constant likelihood. Then if I have a likelihood, we can take the log divided by this beta again. So this is in addition to that. So this is minimal sufficient. So how like we try to reduce it to a thing? The way that you can look at this is that you can try to plot this function. So to plot this function, it would be something like that. And because this is sort of the log of x. Okay, so I have this function, let's say. The thing is, if you give me this function, I can recover the location. So this is going to have kings at the x-axis because it's like p starting with, and the slope changes as you pass any one of the data points. So you can try to plot it, and this shape. And so if you give me this function, I can recover these guys. The thing is, I can only recover the order statistics. I can't tell you which of the xi was the first one. I can just tell you the minimum is this, the maximum is this, the little guy is that. Okay, I can recover from this function. If you give me this shape, I can recover the order. Vice versa, what the statistic can have plot this function because you can see what the based on the number. So based on how many data points you have, the slopes here would be determined completely. So once I have this, you can go verify what the slopes is here and here and here and here. Once you have the list, I guess you can recover this up to the shift. We can recover the very exactly the same, but up to a shift because we only know the slopes. And it's fine, up to a shift means that in the integrated component it's up to the multiplicative factor of the so it's multiplicative factor in the likelihood or the constant shift in the likelihood. So if I recover some of this shift, it's good enough. And it's all in my 50. So this is the shape that you sort of carry all the information that you by relation to the order statistics. If I have the order statistics covering this, if I have a certain probability for this, the order statistics have to be minimal sufficient. Sort of clear. So you have to think a little bit about this, but that's sort of the general idea that the likelihood as a function itself tells you what the minimal sufficient statistic is. Okay, so you have to be able to recover the likelihood from the statistic and the statistic from the likelihood back and forth. For the quadratic, in the case of the Gaussian, you can see that sort of basically the thing is smooth, only there is a minimal location. The location of the minimal tells me this. But I can't recover individual data points from this. This is like you think about this, once I give you the there is like the slope, then the slope, like how sharp it is that it's just this for whether it's like flat or not, and that's determined by n and the location of the minimum up to like so there's no other information in this. There's a lot more information in this. You have all these kinks that you can recover. With the quadratic, there's just the minimum and how spread out it is. And so just n and this can be recovered from the shape of the likelihood factor. Okay. So if you like contemplate these two examples and understand what is going on, it gives you a lot of intuition what kind of minimal sufficiency means. Okay, any questions? Yes.
So it's Gaussian.
Yeah.
In this case, it's a Gaussian, but we know the variance, right? We just
Yeah,
don't know
yes,
its
yeah.
name.
Right.
So the minimum sufficiency changes when we don't know the variance.
Yes, it is. It would be completely different. Yeah, mean wouldn't be sufficient, or the sum. So I think the mean, but wouldn't sufficient there. Okay, sounds good. Okay, thank you guys. I'll come back next time and continue.